Can you hear me? Is the mic good? Okay. So it's basically two experiments I'm going to tell you about. So it's a pretty diverse set of topics I'm going to talk about. But the common thread, keep in mind, it's very sensitive, low threshold detectors looking for weak interaction cross-section process, scattering that happens either neutrino scattering or WIMP scattering. Okay, so there are a lot of big questions. This is a great time to be doing physics. Maybe I saw the light at that time, but there are a lot of unsolved questions. Dark matter, more than a quarter of the universe is dark matter. We have no idea. We've been doing particle physics for a long time. What exactly is it? Dark energy, of course, is a bigger mystery, which, it'll come in the next 100 years. But what's physics beyond the Higgs? As you know, the colliders have found the Higgs. Now the question is, is there new physics beyond that? There hasn't been any new physics in the past couple of years, but maybe there is, Then the neutrinos, they've always been mysterious. A lot of new physics. In fact, the only new physics beyond standard model has been in the neutrino sector. So there are a lot of questions. Why do the neutrinos have mass? They should be massless based on standard model. Is there a fourth generation neutrino? And all sort of fun questions that we can tackle with. And again, let me remind you, my thread will be the detector technology that allows you to do that. So as a lot of you might have heard the first part of my talk, so I'm going to go a little faster. But you know that the stars are moving much faster around the center of the galaxy, and you can pick any galaxy, any spiral galaxy of your choice. So there's a lot of invisible mass that's making these stars move faster than they should. It's not a small effect, it's a big effect. Zwickis looked at the velocity dispersion 80 years ago. Then sort of people forgot. Then 40 years ago, the field got a kick because Vera Rubin made a lot of measurements to all the people. And thanks, Nick, for pointing out I didn't know a key aspect of this. It was really 1970s. That's when people started looking for, thinking deeply about dark matter. So by now we know dark matter exists. A lot of evidence is, the rotation curves, cosmic microwave background, which shows you a very smooth universe, but not completely smooth, and the gravitational lensing, which shows you that there's a lot more mass lensing the light that's coming around it than you can account for by visible part of the spectrum. Then there's, of course, bullet cluster, which shows separation of visible mass that's emitting X-ray from the gravitational mass through lensing. So we know dark matter exists, but what is it made of, and can we detect? So that's the big question. So in that, it's actually funny because astronomers were looking at bigger, farther distances, and the puzzles they were seeing were actually somehow deeply related to smaller particle physics probes looking smaller and smaller. In fact, you probably know that the smallest, if you want to understand the largest, you really have to understand the smallest building block. And in this case, I'm talking about dark matter. We don't know what dark matter is. First, right off the bat, I'll tell you we don't know. It was created, it dominated early universe after Big Bang. Then over the years, over the billions of years, what we have now, we know that the current density is about a quarter of the universe, okay? And if you look at if you try to find out what cross-section would give you the current abundance if they're in thermal equilibrium at some point, then it's the weak scale cross-section. It's a massive particle with weak scale. There's no such particle in the particle, the standard model. So it must be a new particle, it must be physics beyond the standard model. Okay? And it's actually astonishing that we've been doing particle physics for so long, but just realize in the last few decades that what we thought we knew everything is actually the tail of an elephant. Maybe it's not even an elephant, maybe it's a dinosaur. Okay? So the thing I'm going to focus on is dark matter. It's dark, it doesn't interact, it doesn't have electromagnetic interaction, so you don't see it. It's matter because it has gravitational interaction. That's why it's called dark matter. Okay, so so it's a big question. So there are a lot of different ways to hunt for this. You can directly produce it. E equals mc squared. If you have enough energy, you can produce any particle you want. Okay, so that you can produce it in colliders like Large Hadron Collider, or you can look at the annihilation products through indirect searches in space or on ground. Or you can directly collide it. So the way I like to think about it is either you make it or break it, meaning they annihilate, produce something else, or shake it, meaning the dark matter particle would come and hit on your nucleus, on your detector on Earth, and produce a signal that you can detect. Okay, so that's the basic idea. I'm going to focus on direct detection. We live in a dark matter halo, even in our own galaxy. So you're flooded with dark matter all the time. Billions of them pass through you. In fact, if you just want to remember, a bottle might have a few in it at any point of time. They're just streaming right through you. Okay? So the point is, you have this weakly interacting massive particle that's streaming right through you, very low probability of interaction, but there are a lot of them. So when you multiply those two numbers, you can hope to detect dark matter. Okay? So the way to think about it is it's like billiard ball scattering. You have a heavy WIMP moving at a slow velocity. The slow velocity is the key. It's bound to the galaxy. It is slow. That's why it's a big deal, because that's where we can hope to detect dark matter in the current generation, because what they do is they don't resolve individual nuclei. They see the whole nucleus, and that gives a tremendous boost, so it becomes coherent scattering. Okay, when that scattering does happen, it knocks out, it basically shakes, like I said, a nucleus in a crystal, for example, will bounce, and that's your signature. And if you do a back of the envelope calculation for that WIMP and pick any target of your choice, you get a few tenths of keV of energy. That's extra energy. A lot of detectors can do that. That's why there are a lot of experiments all over the world looking for it. Okay? So that's sort of, it's an old map, but it shows you how many experiments are trying to search for dark matter. There are probably 100 big or small experiments, many, many different technologies trying to detect dark matter, because it's one of our biggest questions. Okay, the way we detect dark matter, or we hope to detect dark matter, is pick, let's say, a semiconductor like germanium. If you get a WIMP that hits on it and it recoils, it's going to produce some electron-hole pairs, and because if it's a crystal, it's going to produce some vibration as well. So those are the signal that we hope to detect. If you look at the electron-hole pairs, if you just apply a bias, you can collect the signal and you'll see a pulse. And if you plug in, again, back of the envelope numbers, number of atoms you have, the flux that we know in our local galaxy, and then the cross-section. Cross-section I would just pick right out of textbook, weak scale cross-section, 10 to the minus 42 millimeters. And if I do that, then the number I get is it's very small, but livable. We can deal with it. It's, if you have a 100 kilogram experiment, you're probably going to get less than 1 per day. Okay? So that's okay, but the background, what about the background? And they tend to be the big, big problem, because if you just eat a banana or have a glass of beer, you're going to be flooded with millions of gamma. Just from the potassium 40, there will be a lot of gamma. So that's a problem. So what you do is the traditional technique used by all dark matter experiment or any low background experiment is to put a shield. Layers of various shielding that you design so you can cut down on what you don't want. Those could be radioactive background, but could be cosmic ray background. One easy way to do that is to go underground, because like I said, the signal we are trying to find out is going to be less than 1 per 100 kilogram per day. Okay, so the problem you have is a tiny, tiny signal on. It's like a needle in a haystack problem, huge background. What you have to do is shield appropriately, smartly, and have your detector technology so that you can turn it around and have a giant signal where you have rejected all your background. Okay? So a usual way is to go underground, because most of the background is actually cosmogenic, cosmic ray background. So all dark matter experiments, they all go underground, because most of the cosmic rays, like muons, will stop going through the overburden. Well, muon is a problem because it can knock out neutrons, which can look like WIMPs, the particle that you are trying to. So I'll tell you about 2 such experiments, primarily focus on my experiment, which is Supercdms, but I'll also talk about LUX, which is Bob's experiment. Those are the 2 approved experiments in US, searching for dark matter. So this was a collaboration meeting here last year. The 4 PIs on this experiment are Tobak, myself, Harris, and Mirabal Fathi. We do distinct things in CDMS. Some of us overlap more than the others. Dave is very productive in the analysis, data acquisition, and electronics, and the rest of us work on detectors and analysis as well. So what's the big picture of this detector technology? What you have is a slow WIMP coming and hitting on your nucleus coherently. It doesn't see the individual nucleon, so it sees the whole nucleus. Okay, and this detector, that's at very low temperature, about 40 millikelvin temperature. By the way, when you're done, if you want to look at detectors, feel free to come over. So there are intricate sensors on top of this and the bottom, which detect the tiny vibrations and the electric ionization signal that I told you about. And they produce pulses. Okay? What it does is then the ionization and phonons, they produce two nice bands, because that, at the end of the day, you have to reject your background. This is the background, this is your signal. You can say, how do you know that's your signal? Because you have never seen WIMPs. These are neutrons. Neutron would behave like WIMP, like I said. So these are calibrated using neutrons, these are calibrated using gamma. So it's a beautiful separation between signal and background. Okay, and then you take this beautiful technology and shield it in various layers of poly and lead to protect against neutrons and gamma. So you do that, then you put it in the middle, it's cryogenically cooled, and you get beautiful separation between signal and background. The question is, when do you see the WIMP? That we'll see. Nobody has detected WIMPs yet. Okay, so in our detector, what happens is, when there's a particle recoil, you produce electron-hole pairs. This is a little more detailed. Then what happens is, because of the electric field, they drift, and when they drift, they themselves can produce phonons. And there are also phonons, high-frequency phonons, that are produced, which scatter and down-convert and produce more phonons. At the end of the day, we measure two kinds of signals: ionization, that's pretty fast, and phonon signals. Those are the two measures that we do measurements, so we can tell whether it's a signal or background. The ionization is easy. The phonon sensors, it takes a lot of effort and a lot of design work. If you pick a detector, there are about 4,000 sensors. You zoom in on one, this is a unit sensor. There's a large antenna-like thing, and there's a sensor in the middle. The way it works is you look at inside the crystal. When there's a particle interaction, there are phonons produced in the crystal. Okay? Those phonons have enough energy to break the Cooper pairs in aluminum. The aluminum superconducting band gap is about millielectron volt. So these phonons break those Cooper pairs, and the tungsten can trap those. There's a lower band gap. And if when they trap it, what happens is the tungsten its TC is designed so that it's sitting right here in this transition region. There's a little more detail if you're interested. I'll tell you after the seminar. But we design it in such a way, a small current is dumped, we hold it in the maximum slope area. Okay? So when there's a small deposition of energy, what you see is a small change in temperature and a small change in resistance. If there is a small change in resistance, there will be a small change in current flowing through it. And that's what we pick up through screws. That's how it works. And this was, the pioneer in this was Blas Cabrera at Stanford, who has been a long-term spokesperson, now the project director. Okay, so what's our hunting ground? That's beautiful. That's a beautiful detector technology. And I'll tell you about the Lux detector technology. That's our hunting ground. Let me set the ground. I'm going to spend a minute on this slide because it's a very important slide. This is a WIMP nucleon cross-section on the y-axis and the WIMP mass on the x-axis. So all these curves, they means some experiment has excluded any cross-section above that, because if the cross-section were higher, we would have seen it at 90% confidence. Okay? There have been a few false claims, but nothing has been found. Nobody has found anything. There are a few things to think about. That's about the weak scale cross-section. That's a broad area that we are looking for WIMPs to be there. Okay? And the WIMP mass, we don't know what the WIMP mass is. So it's a very broad search. The two experiments I'll tell you about, Supercdms for low mass, Lux LZ for high mass, but that's our hunting ground. Okay? That's where we're going to search. The thing that you notice is there's a floor here, neutrino coherent scattering. And that relates to the second part of my talk, why I'm interested in that process. Eventually, as you look for WIMPs, go down, explore this space, design better and better experiments, at some point you're going to hit that floor. Luis Trigari was the first one in the community to realize there's such a floor which all dark matter experiments will eventually hit. Okay? So it's very important for us to measure that even before we get there so that people believe we can search for WIMPs beyond that floor. It's not a hard floor. Okay, so nobody has detected any WIMPs yet. So what is the strategy? I showed you in the previous plot that we want to explore all this space that has not been explored yet. So to go down, what you really need to do is make bigger and bigger experiments. If I make a 10 times bigger experiment, I'll go down by an order of magnitude. There are a lot of orders of magnitudes out there, okay? And that's something we can do, because if you look at the rate, number of events that you see, there are a few multiplicative factors there. Number of nucleons times the flux times the cross-section. This is something we have under our control, of course, given a limited budget. There's the other guy, flux and cross-section. You have no control over it. So what we're going to focus on is make bigger and better detectors within a reasonable cost. And that's what we have been doing since I joined Texas A&M a little less than 8 years ago. We have gathered lots of donation from the industry. Most of this equipment that you see, more than $3 million worth of equipment, they were donated by semiconductor industry. And they're good for our next generation as well, because those are 6-inch capable equipment. They can make 6-inch diameter detectors. Okay, so the way it works is basically take crystals, align them with XRD, polish them, make them flat, put various thin layers, because the circuit that I showed you, they're made of thin film. Very standard semiconductor technology that people have perfected over many, many years. So we do that, and what you do at the end of the day, when you process them, you get your detector. Okay? I do encourage you to come. If you're interested, you can visit our labs and see how these are actually made. I'm going to show you a couple of steps. This is the heart of the project. We have the detector fabrication project. This one does the thin film deposition. The breakthrough came when we set up our lab. This machine made a lot of things happen very, very well, because it could make a lot of detectors quickly, make it very uniform, make the sensors much, much better. Okay? Then what you do is, after you take the thin film, then you can make a photosensitive coating. It's like taking a film. And this is your circuit that you want to make on your crystal. And then if you do exposure and developing just like a film, now you see a detector being born. You see the circuits. It's pretty standard semiconductor technology, which makes you wonder why we haven't done it a long time ago. That's a different story, but it has been, we have made these changes, we got good instruments, and we have tremendously improved the superconducting temperature uniformity over a large crystal. It used to be 20 millikelvin, now we've gotten it down to 2 millikelvin. And that's very important as you're trying to make this transition as sensitive. Okay, so that's not the only thing. What we've done is, because of the process expertise we have with our faculties, we have actually performed detailed investigation to make the process much better. Just to give you an example, the phonons break Cooper pairs, and the quasi-particles are trapped in tungsten. They go like this. The better connection you have on the sidewall will give you a better signal. So we actually did SEM imaging, systematically studied how to improve it, and eventually got a design that has much better connectivity than we had before. And of course, this passes on to Stanford. They have adapted the same process development as well, and it works beautifully. Okay, so now coming back to performance of these detectors that we made. I'm showing you a plot of the first detector that has achieved the Supercdms snow lab spec. When we design an experiment, we say that we're going to hit this cross-section within 3 years or few years with this much mass. A key factor in that is the noise or the resolution. Okay, so the resolution that we achieved with our detector that was made at Texas A&M, it basically achieves the key performance parameter, we call it, for Supercdms snow lab. It's 50 electron volt resolution. Okay, so that was great news. This was done 2 years ago. I'll tell you a little bit about the process, why it's so important, why Texas A&M has played a leading role in this experiment, is because of a lot of process expertise we have had that has really reduced the cost from $500,000 per detector to about $50,000 per detector. If you're going to span 2 orders of magnitude in the cross-section space, nobody is going to give you 2 orders of magnitude more money. You have to find ways to improve, reduce cost, and do better. And this is one of the ways. You reduce the cost by having more success. For industry, if you get something like this, that's still salvageable, because each unit is what you want to use. You can cut it off and use it. That's a disaster for us. When our crystals or wafers, when they're produced, they're called the golden standard by industry because it is mostly successful. Okay? So now I'm going to switch gear and tell you about the two dark matter experiments, what their projected sensitivities. We're working hard to actually build the experiment. Bob is on the LZ experiment, and I'm on the Supercdms experiment along with other faculties that I told you about, Toback, Mirabal Fathi, and Harris. The two experiments that have been approved by DOE and NSF, the community has selected us to be the two experiments focusing on two mass regimes, light mass WIMPs, heavy mass WIMPs. And there's a reason, which I will explain to you. So those are the two approved experiments in the US. There are, of course, many other competing experiments in Europe and China and almost every country has an experiment or participating in an experiment. First, I will tell you about the LUX experiment. That's leading the world, has been leading the world for a couple of years and will continue to lead in heavy mass WIMP search. Why? Because it's a really cute technology and it's a simpler cryogenics. The problem with the cryogenic detectors that we use, millikelvin, is the fridge always becomes a bottleneck. Whereas in this is a much simpler cryogenics. It's liquid nitrogen temperature. You cool it down, then what you have is this is a cylinder, imagine, with liquid xenon. If there's a particle interaction, it's going to scintillate. Xenon scintillate. Particle interaction produces scintillation and also produces electrons, just like CDMs. So you see some light with PMTs on top and bottom. Then as these electrons drift with high voltage, they eventually get to a gaseous phase where they amplify because of the high voltage. They produce many other photons, electrons and photons. And that's what you see as the S2 signal. So by using two signals, just like CDMS, you can develop projection. So that's your background, this is your signal, and you calibrate that. The beauty of this technology is because it's so dense, xenon is very dense. So it protects the cell from radioactive background coming from the side. So if you look at the central volume, it's essentially quiet. It's a beautiful technology, very scalable, and that's why it's leading the world in heavy mass WIMP. This is a time to remember James. He was a pioneer in a lot of this xenon technology. His lab is right next to my lab. We still miss him, even after so many years. He was a key guy in developing many of these technologies. And Bob has taken over and continuing the tradition. I'm going to go on to CDMS, Supercdms. I'm going to just use this arrow because it's not working out very well. Okay, so I'll tell you about Supercdms. Supercdms has been an experiment that's been operating in Sudan Underground Lab in northern Minnesota. Now, for the next generation experiment, we go to a warmer place in Canada, in Snow Lab. Okay, it's actually a little south of Minnesota. Minnesota is one of the coldest places in the U.S., if you didn't know that. And the technique is, again, very standard. You have your detector at the quietest place you can make with various layers of shielding, lead shielding to protect against gammas, poly shielding to protect against neutrons. And you build this shielding and put your detector in, and then you make the advantage of CDMS technology is we do have our unique strength. Our advantage is we can make each detector is like this, about 1.33 inch by 4 inch. So you build a lot of detectors. Unlike xenon, which you build one monolithic detector, because we build individual detectors, the performance can continue to improve throughout the project life. In fact, you could even change the material depending on what, let's say, LHC finds WIMP with a certain cross-section with certain properties. We could choose the material that is the best cross-section for that. Maybe the physics, the field theory, that the effective field theory that is actually obeyed by the interaction is so different from what we thought, we may not even use germanium in 2 years from now. So the key thing is our detectors can be a new detector every day, okay? So that's what makes it very exciting. Now I'll tell you what we want to do and why it's so difficult. So this is where we are. This is where we are. This is where we want to go. So this is where we are. This is where we want to go. You see, that's many, many orders of magnitude. 5, 6 orders of magnitude. If it were easy, we would have done it a long time ago. In fact, it's not easy. There's a reason why all these sensitivities dive up. The reason is, imagine you're driving a car, somebody threw a tennis ball at you. You wouldn't notice it because the tennis ball is very small mass. It doesn't transfer a lot of energy. Okay? But if you're hit by a massive lead ball, you would have probably noticed it. Okay? So that's the idea. That when you probe low mass WIMPs, it's very hard because your threshold is not good enough to even notice it. So that's what we're going to focus on, and I'll tell you in the next 10 minutes, and then go on to the neutrino experiments, how we can utilize that to do this and that as well. It's the same process, essentially similar process. So let me first explain to you why it's so hard. If you take a 100 GeV WIMP, heavier WIMP, this is what happens, the recoil spectrum that you would see in different material like xenon, germanium, silicon, argon, neon. You get recoil energies up to like tens of keV. You make that a lighter WIMP like 20 GeV, most of them are gone by 25 keV. You make it 10 GeV, there's nothing above 10 keV. To remind you, when we had Cdms experiment, our threshold was 10 keV, meaning we were looking at above this. We would have never detected low mass WIMP. So what's the plan? You have to integrate, so you have to lower the threshold. Okay, so you can be sensitive to this recoil spectrum. And that's not enough. That's not the end of the story, because your background can kill you. If your background is higher, it doesn't matter what threshold you make. You will never see anything. Okay? So that's what we've been working on. But it's actually, again, it becomes even harder, both germanium and xenon. There is a factor called Lindhard. When you have nuclear recoil, because we are looking at WIMPs, which make nuclear recoil, the signal that you see, the ionization signal, is actually small. With 100 EV recoil, you only see 7 EV. Extremely small signal because of multiple penalty factors, as you see. So that's called a Lindhard. You see, it's a small factor. So it's a very small ionization. If I really want to search for less than 10 GeV WIMP, I have a very small signal to work with. So what we do is we use a phenomenon called Meganoff amplification. If you apply high bias, these electrons that are drifting across the crystal, they themselves can produce phonon. So it's like an amplifier. You are increasing the voltage and you get more and more signal. That's like magic. And in fact, it does happen like magic. That you increase the voltage and you get more and more signal. That's called the loop amplification. Supercdms already uses it. Unfortunately, it doesn't work like perfect magic. It stops at about 25 volts per centimeter, then you get huge noise. Okay? And we have actually made tremendous progress at Texas A&M dealing with this. In fact, the plot that you see is the world record in a large mass germanium detector. It has 7 EV resolution. Okay? And you see the noise doesn't change, the phonon noise doesn't change with bias, whereas the signal grows. It's like the ideal setup. And this was done in collaboration when Mirabal Fatih was at Berkeley. This detector was made at Texas A&M. And this is your ideal detector. But this was done with a special vacuum gap so that there is no breakdown on one side. This was to understand what is the reason why these crystals develop breakdown. Okay? So with all these technologies, what I'm showing you, we're very proud of this. That's the first Supercdms high voltage detector. It was fabricated 2 weeks ago. It's a gigantic, it's actually from our perspective is big. It's 1.5 kilogram, 4-inch by 1.33 inch. That's the first germanium high voltage detector. It's at Minnesota now, being tested. And then next we moved on to fabricate silicon high voltage detector. Okay, so that's, these things take a lot of effort, a lot of people. In fact, there are the two distinct groups we have, the device group, which looks at all the details. Why does a layer work better in blocking leakage? How do you get a better waterfall or a better phonon connection? How do you make detectors that are more stable or have better resolution? These all take painstaking work, detailed investigation. These are the people that participate in that. And our cryogenics group, low temperature group, that actually will be doing pretty soon. They've done some sample measurements, but soon they'll be doing full detector testing. So you can close the loop very quickly. Because imagine you walk out of your lab having a detector, test it in the next room, come back, you never get what you want, then you come back, make some changes. It's a very rapid feedback loop that will definitely help us move forward very, very well. Okay, so that's, sorry. I gave away. All right. So yeah. So the thing is, this becomes, once you have this detector, amazing detector with very low threshold, large mass, they become like Swiss Army knife. Okay, because there are a lot of things you can do with. Okay, it's not just dark matter. In fact, I showed you that there is coherent neutrino scattering floor that people have to investigate. So we saw the opportunity, and this is something that has been proposed for 30 years by many, many people trying to detect coherent neutrino scattering. So what we're going to do at Nuclear Science Center, which is a megawatt reactor, we're going to have the neutrinos coming from that scatter on our detector, as simple as that. This is exactly the same process, similar process as the WIMP scattering on our detector. Same low threshold detector technology is needed, but not as stringent requirement on background. That's why we can do it so easily. So we have a collaboration now that formed about a year ago. There's more than 50 people, 4 countries, many, many universities. This was really the result of the strong synergy we have in the institute and at Texas A&M. Like I said, none of us have had the expertise to bring up a whole project. There are a lot of people who contributed, who really seeded at Texas. I'm the spokesperson of this collaboration, but there are a lot of contributions from many, many places, University of Minnesota, UT Austin is a large group, very large contingent. We have on Monday our next collaboration meeting at UT Austin, minor collaboration meeting. Okay, so what is the big deal about coherent neutrino scattering? It's actually very connected to the WIMP history. 30 years ago, Blas Cabrera, Lawrence Krauss, Frank Wilczek got the 2005 Nobel Prize. Yeah, so they proposed 30 years ago to look for neutrino scattering on silicon detectors. Okay, now this is very relevant. If you want to look at solar neutrinos, for example, or if you want to look at dark matter, eventually you have the solar neutrino flow for us. And for Bob, it's the atmospheric neutrino. The coherent neutrino scattering is very, very relevant to us. That's where you want to measure it. Now, I'll tell you a few reasons why we're investing time and effort into doing that. First of all, it has never been done. It's kind of fun to be the first one to do something. But it is the WIMP search background. That's why it's very, very close, dear to our heart. As we are searching for WIMPs, we want to measure that so we can be confident about the generation 3 experiment. If there's any deviation from standard model, if you measure this cross-section that's been predicted by standard model, that could mean new physics, maybe a Z prime. Okay, that's contributing to the Feynman diagram. There's been a lot of measurements at various experiments looking for neutrinos. It's basically what's called the sterile neutrino problem, the 4th generation. Maybe there's a 4th generation neutrino. Sterile, it doesn't mix with ordinary neutrinos the same way as the 3 neutrinos mix with each other. So what you see is, if you start with a certain spectrum of neutrinos, you see some neutrinos have disappeared. Okay, this is what you expect, this is what you see. A lot of experiments see that. So could it mean new physics? You could say, oh, it's just, you don't know what one means, right? That could be as simple as that. So we are taking a different approach to seeing that. Not to be fooled by what is one, the definition of one, but I'll show you in a minute how we can address that question. It's also important for supernovae, because that's 99% of the energies go into producing this MeV scale neutrinos. Our dream, of course, is to convert our detectors to do astronomy, neutrino astronomy, solar and supernovae neutrinos. Now, coming back to this coherent neutrino scattering process, this is a standard model flavor-blind Z0 process. The Feynman diagram looks like this. So it's predicted very well by standard model. Look at the cross-section, that's big. The cross-section I showed you that we've already investigated in searching for WIMPs was much lower than that, by 3 to 4 orders of magnitude. But nobody still has detected this, for a simple reason. If you look at the events, you hardly see any event above 1 keV. That's an EV. Above 1 keV, you don't have any. That's the reason why people haven't seen it. Well, once you have a technology that allows you to see it, this becomes one of the best probes for new physics. And neutrinos, as you know, they're always surprising. They have new surprises every time somebody has done a neutrino experiment. Even as recent as theta 1-3 in the array, people thought it would be small. It wasn't small. Okay, there are amazing surprises everywhere in neutrinos. Okay, so let me tell you a little bit about the sterile neutrino. That's a recent plot. Like I told you, many experiments all over the world, when they look at neutrinos, they see that there's some fraction of the neutrinos are missing. Either their calibration is wrong, meaning your normalization is wrong, or you have a phenomenon going on where the neutrinos just disappear into a sterile neutrino. Okay, and that has a diabase result as well. And this seems to be the best fit, 3+1, 3 standard neutrinos and a sterile neutrino. If this is the best fit, the best fit mass for the sterile neutrino is a EV mass. Okay, so how do you look for this thing? Right away, I'll tell you that the problem of normalization, if you just look at the total, you might not have your normalization right. But if it's really oscillation, it appears to oscillate very quickly. So if you can have a very short baseline experiment, which nobody in the world has ever done, a very short baseline experiment, maybe you'll be able to see the physics that's responsible for this. Okay, so how do people look at neutrinos? All the neutrino experiments so far, they have looked at not the incoherent process, either the charge current process, the inverse rate decay, or neutral current scattering experiment. This is why you need gigantic detectors, kiloton detectors. But if you look at the coherent process, then you don't need that. Immediately your kiloton can be done. You can do the same thing with the detector light. Why? Because the coherence has a factor of a to the power 4. So that gives you a tremendous boost. Okay? So you can squeeze it down into a tiny detector and still be able to do that. That sounds amazing. It's actually true. But the problem is nobody had the low threshold needed for seeing or detecting the coherent process. And we do. And we have already demonstrated that we can have the threshold. So what we're going to do, the idea is very simple. Take our detector, put it next to the reactor with the appropriate setup and shielding, and then you might see what you're trying to see, new physics. If not, either it could be just standard model process, that would still be cool. The main idea is that our reactor is unique. There's only, very rarely do you see a core that can be moved. And that's going to be the key to our detecting or excluding the possibility of sterile neutrino. There are a few key features of our reactor. We do have the detector, but the other cool feature of this is the facility allows us to put the detector right next to the core, as close as 1 meter. Nobody else has ever done that. Okay, and why is that important? Because if you just do the simple math, the flux, neutrinos, they're coming out with a isotropic direction. If you're 1 meter away, what you can do with 10 kilograms, if you're just 100 meters away, you need 100-ton detector. That's just mind-boggling. So being very close to the core allows us to have a small detector and still get the same physics. Okay, so now I'm going to go through and show you some experimental slides, how this is going to happen. There's an experimental cavern that we're fortunate that it already exists, so we can stick our shielding and our detector in there and get very close proximity to the core. Okay, this is another visual. That's the core, and we stick our detector into this cavern. That's what the cavern inside looks like, and get very close to the core. The big problem with a nuclear reactor, as you can guess, is a lot of background. It is gigantic, 10 to the 15 per centimeter square per second. You're blasted with gammas and neutrons, huge amount of gammas and neutrons. So the key then is, yes, you can get very close, but you're going to be flooded with background, okay? So we don't get extremely close, but we get fairly close. So we optimize, we design shielding and see what we can live with, okay? So that's what we've been doing for the past 1 year. Because in the past 1 year, let me remind you, standard model predicts the signal very, very well. We don't really have much uncertainty in that. If the uncertainty is really in the background. If you can beat down the background, design shielding, then only you can do this cool physics. And that's what we have spent the last 1 year. And what you see here is the actual measurement in situ with a certain shielding matches very well with the Monte Carlo. So that has allowed us to design the full shielding for the actual experiment where you don't want the neutrons coming out of the core. They're blocked by the poly. You don't want the gammas, they're blocked by the lead shielding, but you do want the neutrinos to scatter in your detector. Okay? So this, again, is an important slide. What I'm going to show you here is we already have the detector technology. Okay, I showed you the problem, why nobody has ever detected this process, because of, nobody had a detector technology that goes below 1000 eV, so that's 1 kV. So we already have that problem solved. Okay, so we do get sensitivity to all this interaction. Then the main problem or main uncertainty was the background. If the background were higher, you would not see that. In fact, the background was up here when we started. Okay, then we had to beat down on the background by designing the shielding to get to an acceptable level so that you see, so you still have a lot to integrate. The problem is much more simpler than dark matter. The dark matter, I told you, the rate is less than 1 per 100 kilogram day. Here, the rate is 10,000 per kilogram per day. You're flooded with signals, so it's not such a big battle with background. You don't have to beat down on the background. In fact, our background design, the shielding design, is about 1 million times looser than our dark matter experiment that we're already doing. So it's at a level now where we are confident we can discover CNS, we can make measurement, and our prediction is, depending on the optimistic versus pessimistic scenarios, within 1 to 4 months of actually turning on and taking data, we will be able to measure CNS for sure. You know, people have been trying it for 30 years. Of course, you always see unforeseen problems, but even in the worst case, as soon as you start taking data with a fridge in there, we should be seeing it within a few months. Okay, but the actual discovery of new physics beyond that, when you use the CNS as a tool to detect or try to detect new physics, that will take much more time, maybe a year more. So we just published or submitted for publication our first minor paper that's on the background. Because in the community, by the way, the community has a lot of experiments, more than a dozen experiments trying to do what we're trying to do. There's no uncertainty on the signal. It's always about the background. Okay, so we have lots of shielding. The way we try to pull off this experiment is by getting everything for free. And we, you know, if you were to ask for funding, such an experiment would cost many, many millions of dollars, which we don't have. Okay, so what we did is timing was good. Supercdms Sudan ended. So we got a lot of electronics and shielding and fridge from that, and also the UT Austin folks got the NOVA. They were involved in the NOVA experiment, neutrino experiment. So they got a lot of liquid syndrome stuff. And so the DAC, the data acquisition, is being set up. They'll be brought here. Now, what I want to do in the remaining 5 minutes is show you the beautiful physics we can do beyond standard model. I showed you we can definitely detect coherent neutrino scattering within a few months of turning on. But beyond that, what do you do? So once you detect coherent neutrino scattering, if there is a 4th generation sterile neutrino with a short baseline oscillation, that's the kind of spectrum you're going to see. They disappear, reappear, that's the oscillation, okay? And I'll show you the cartoon of what we expect to see. That's the top view, that's the core. Our experiment is here. The core can be precisely moved. It actually takes only half an hour to move to a new position, thanks to the beautiful facility we have at the NSC. So watch carefully as I move the core, what happens to the signal. So you're seeing certain rate of neutrinos. That's the behavior you would see as you move the core. And this has nothing to do with missing normalization, right? If you're just looking at normalization or the level, then you could be fooled by not knowing the normalization. Here you see a telltale signature. Maybe there's no new physics. Maybe there's no sterile neutrino. But what's our sensitivity to that? If there is a sterile neutrino, we would see it at the level, the world average. We'll see it within a year, okay? And then what I show you is, if there is no sterile neutrino, or not at the level that people think, then in a year, we can be the world-leading experiment in about a year. These are the proposed future experiments, by the way. And it does include the world average various points. And if you want to know more about it, please see us after the colloquium. If we continue to do this experiment and get funded and do the next phase, we will be the best for a decade. Okay, you would do a much bigger experiment. maybe 100 kilogram to a ton, you will be better than even the proposed experiment. Okay. So now let's look at the Z prime. So Z prime is an additional Feynman diagram. So that's your Z process. Then there could be additional Feynman diagrams that add to your rate. This is something that LHC looks for in dial-lepton channels. So if you have an additional contribution from a mediator, then you would see it in your rate. Okay. So LHC has a sensitivity that they can reach up to 4 GeV or so. That's sort of max out. They are not sensitive to Z prime beyond that. In a minor phase 1, we're competitive with LHC. And in phase 2, we'll be much better than LHC. If LHC doesn't get an upgrade, we'll always be better than them. Now, let me tell you what is the signal that we expect to see. That's your standard model, Z0. If there is a Z prime, if it happens to be 1 TeV, I'm just showing you the scenario, there will be an additional contribution. But that's huge. That's a big signal. We can surely detect that because that's above our node. If you want to probe heavier and heavier Z primes, as we want to, you see that the additional contribution goes down as you go to higher and higher Z primes. So if you're really being ambitious and pushing 10 TeV, what you have to do is the uncertainty on this needs to be small so that you can see the new physics. Okay? And at that level, as an evolving process, we'll get better understanding of our background so that we hope to push on this down to 10 years. Okay, now something more. Like I said, it's really a Swiss Army knife, this detector. You can look at the neutrino magnetic moment. This is the standard model process. If you have a big neutrino magnetic moment, that's the modification to the signal you'll see at low energies. At very low energies, you're going to see exit. Okay, and in fact, let's pretend that it's the neutrinos are Majorana. Okay, we don't yet know whether they're Majorana or Dirac. If they're Majorana, they could have large magnetic moment. And if we do see something like that, that could become the first hint. It's hard. I'll tell you why it's so hard. Because to get to a sensitivity that's better than what you already have from astrophysical limits, you need a lot of mass and good threshold. It becomes harder and harder. That's a hard game. But in the phase 1, we can be the best in the world, beating the current best, gamma. Okay, so there are also nuclear physics things you can do with this. It's not just Z prime and sterile neutrino. And this is why Grisha is in here. He's on the collaboration because he would like to find out the form factors of neutrons, right? So I put your picture there. I don't have time to go through. You should talk to him afterward. So who are the competitors to minor? Like I told you, there are a dozen experiments in the world looking for coherent neutrino scattering. Some of our biggest competitors are coherent experiment at Oak Ridge. What they do, their advantage is they have neutrinos that are higher energies, and your endpoint goes a square. So it means they don't have to fight with detector technology that are as sensitive as ours. So they have much bigger energy to play with. So, but still they haven't been able to see coherent neutrino scattering. They're pursuing many different detector types: germanium, cesium iodide, sodium iodide, liquid argon. They had a liquid xenon as well, which was going to come from Russia, but it was banned by the government. It couldn't leave Russia. Okay, so their major advantage is the harder recoil. So they may beat us to the coherent neutrino scatter. There are also other experiments like Prospect at Livermore. What they do is they have a big detector. They don't look at the coherent process. They just look at the inverse beta decay. And their idea is cool. They're going to detect the neutron using a lithium-6 doped liquid simulator. So they will see very clear signature. Unlike our core moving, they're going to move the experiment. By the way, this is a gigantic experiment. So what they're going to do is look at the distance oscillation in their detector. They are different cells. So they're going to see if there's oscillation within the cell, among the cells. Okay? There are other experiments. I'm running out of time. Texano in Korea, there's China, a lot of experiments. Then now what I'm going to show you is when you see you're standing in the field for your experiment, when other experiments that are your competitors, how they perceive you. So I thought it was cool. They just pulled up a talk, recent talk. Coherent spokesperson gave a talk. So he highlights some of the leading experiments that she puts mine. Okay, so I'm going to end the talk with talking about the synergy. Why are we doing this? Why are we pursuing two different experiments? And there's a value in that, because if you're going to build that amazing detector, you might as well take full advantage of it. Because we want to go there. Eventually, we're going to hit the coherent neutrino scattering field. And in fact, we want to go beyond that. So we want to definitely measure that very, very well. Okay? So it's the same detector technology that benefits minor and vice versa. Whatever we develop for minor, it gets application in the dark matter experiment as well. So it works out beautiful. And the coherent process is just beautiful, because with a kilogram, you can detect what you would need a kiloton to detect. Okay? So it's an excellent source for BSM, beyond standard model physics. And eventually, you want to hit the solar neutrino floor, try to understand the CNO cycle in the sun. It's just a lot of cool things we can do. And like I said, we definitely want to hit the point where we can detect supernova neutrinos. So, but now I'll end with a little sad note, meaning sad for us, obviously, as a community. There's been no sign of dark matter. From indirect detection, we've already passed the thermal relic density. This is a cross-section, basically, cross-section times the velocity. In dark matter mass, nobody has seen anything. In colliders, nobody has seen anything. There's been no sign of dark matter. Where is it hiding? So, you know, the way I like to say, it took 100 years to understand 5%. It's not surprising that we are not finding the answer yet. It's going to take a lot of ingenious effort, a lot of persistence to go through various experiments, systematically try to explore the parameter space, and then see what new physics might be out there. So the current generation experiment already are exploring some important parameter space. The next generation experiment, approved experiment, Supercdms and LZ, they will cut through a lot of interesting parameter space. Some of them will even hit the neutrino field. So it's I feel very privileged that we have a team here that has a lot of expertise that helps us quickly gather, move quickly, and come up with new ideas. And I'm very hopeful minor will be the first one to detect CNS. We'll see what new physics is out. And I am always very aware, you may never find what you're set out to look out for, but you may find something else that may be even better than what you thought. Thank you. Yes. We don't know. So it's basically you start with the simplest hypothesis. The dark matter behaves like a weakly interacting massive particle. They scatter with a weak interaction cross-section. In fact, what you said is there's even a closer to home truth. Dark matter may not even interact with, let's say, through Higgs, for example. It could interact with Z0 or some modified field theory that it operates through. So you may not see the interaction process that you think it is, but you start with the simplest one. Let's say it's a Higgs interaction. Then you search for it. Only after you find something, then you backtrack and see what could have come from. Until you see something, you're in the dark as to what might be the interaction. Any hypothesis? Sorry? Yeah. You'll be in dark if you don't see anything. Right. So only if you see something, then you try to find out what theories fit that, fit what you see. Yes. Oh, because they're bound to the galaxy, right? So you take this heavy dark matter particles, they're bound to the galaxy. So it's basically the way to think about it is, on an average, dark matter is at rest. The thing that's really happening is the sun is going around the center of the galaxy, is the sun's speed that you're plowing through the rain, essentially. It's about 200 kilometers per second. So dark matter, you can essentially think of them as rest. It's an actual Boltzmann distribution. Mostly at rest is the sun as you're going through. on Earth, you are hitting the dark matter with 200 kilometers. So it'd be amazing. If it's actually faster, it's great because it's more likely to be detected. In fact, with dark matter, when you take the standard hello assumption, it's actually very sensitive because you're mostly detecting the tail, the faster particles. Because the slower particles, they are below your threshold, unless you have a beautiful low threshold detector. So yeah, so there are uncertainties in what's the velocity of dark matter. If it's faster, it's always beneficial. The worry is if it's slower. Yes. No, it's actually, that's a good question. It's very large. We're actually 20% of the whole collaboration. We have about 20 people. We have 4 postdocs, 4 PIs, engineer, technician, graduate students. So we're the largest in the collaboration. Our contribution, if you measure in terms of the detector, like I showed you, we're the only ones now making detectors. Stanford and us, we should be making detectors. Right now they are having some troubles. But yeah, the contribution is we just made the first detector and we're about to make the second detector. And there are a lot of other things like Dave should give a talk on his contributions on the analysis front. They're leading the whole analysis effort from Supercdms Sudan. Mirabal Fathi, he has come up with beautiful ideas on, one question I often get asked is directional. How could you at the end of the day know it's really dark matter? One clear thing, like coming back to Alex's question, as I said, sun is moving through, plowing through the galaxy. So if anything, directionality would be the best way to cut down on background. But can you make a directional detectors? That's a topic for another seminar. He has come up with a beautiful strategy on how you can take advantage of the efficiency of different crystalline planes to detect directionality in a detector. And the miner would be the best place to look for it because the neutrinos are coming from the core. So if you can demonstrate it there, then you know that you have the most amazing technology. Thank you.